All right, section 3.2, we're going to take a look at addition and subtraction. We're going to talk about some of the theory underlying the things that you know. We're going to talk about different models for addition and subtraction. And the idea behind what we're doing is taking a look at, in particular today we'll do addition, different ways of thinking about addition, so that if you notice a child is having difficulty with addition, like with word problem kind of things, you might actually be able to decipher if it's really the addition that's causing the problem or the way that the question is phrased. That's the kicker. Because our kids come to us with different experiences, and sometimes just the wording of something will throw students off when the problem was very simple. They just didn't see how to work it. In fact, it happened to you, right, Savannah? The problem wasn't really hard. You just weren't sure what the point was, and so you weren't sure how to process the question. So we're going to take a look today at addition. So this is the definition of addition of whole numbers. We're going to let A and B be two disjoint finite sets, where the number of items in set A is A, little a, and the number of items in set B is B. Disjoint, if you're thinking about in terms of Venn diagrams, means that the circles don't overlap. Okay, there is no intersection. That's what disjoint means. Then, if we were to add A and B together, lower cases, it would be the same as counting the number of items in the union. And the reason that's true is because they don't overlap. The numbers A and B are addends, as we call them, and A plus B is called the sum. Okay? So the first thing we're going to take a look at is why it's so necessary that these be disjoint. So it says, give an example to show why in the definition A and B must be disjoint. So in particular, what we're going to do is we're going to create a set A and a set B that are not disjoint and show that we would have a problem if we tried to do this. So we're going to simply create a numerical example where we can count it easily of items in set A. So somebody give me a few items to put in set A. Let's do numbers just so it's easy to count quick. 1, 2, 3, 4. Now, I need to make a set B that overlaps this. So pick something or some things from set A that I can put in set B. 3, 4, 5, 6. I'll put a 7 just so that you don't think that somehow they have to be the same number of items. They don't. Okay. So what we learned about in chapter 2 is that we can write this notation like this, which simply means the number of items in set A. So how many items are there in set A? 4. How many items are there in set B? 5. Very good. Now pause for a moment over there. We're going to also find now the union. What is the union of set A and B? What does union mean again? All the numbers included, right? Not the overlap, but everything included. So what would it be? Cool. And the number of items then in that union is what? It's 7. But what is it when we add my 4 and my 5? I get 9. And these are not equal. That might be the shocker of the day, right? You had no idea. 9 and 7 not equal. So why did that happen? Well, it happened because when I counted set A, I counted numbers 3 and 4. And when I counted set B, I counted numbers 3 and 4, right? Double counted things. And that's why it has to be disjoint for this definition to make sense. All right, there are 3 models for addition that I'd like for you to learn about. The first model for addition is called the set model. I said 3, and I mean 2. Sorry, two models. The set model is typically used for whole objects. And this would be an example of something where we count an object as a whole. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So the reason this is a set model is because even when crayons are sort of going down, right, we still call it a whole crayon. You know what I'm saying? I don't look at it and say, oh no, you've used like a tiny little piece off the top, so now it's 9/8 or 9/10 of a crayon. We don't do that, right? We count it like it's a whole object. It's an object that's counted as a whole. And there's plenty of things you could do that are like that. The example that I had done and absolutely did not mean to miscommunicate, Cameron was the one who came and asked me about it, was the problem on your test about feet, right? And I meant feet like sets. They're an object, right? But our other model here in a minute is going to talk about it like it's distances. And that's a different type of a description, different type of a problem. So one of the ways that you can actually do these kind of problems is that you can use concrete models, especially when kids are really young learning. So thinking, pre-K, maybe kindergarten, depending on what kids are coming out as or into your schools. And what you can do is you can actually draw pictures or use physical objects, like I passed around my physical objects for you, to show what addition looks like. So if I had, what did it say? 3 blue crayons, I can actually draw 3 blue crayons. They don't even have to be the same size because, like we said, the crayons aren't always the same size. And I have 2 red crayons. So I could actually draw them. Whoa. And then we could look at counting how many are here, and there are what? 5 crayons. And every time we're working with problems with context, there should be context in your answer. So the answer is not 5, the answer is 5 crayons, okay? Now, this is different than the other model. The other model is a number line or a measurement model. It's typically used for objects that can be partitioned. For example, Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? It's a very different question. It's still addition. Really, the answer is still 3 plus 4, right? I mean, there's nothing about it that really numerically, calculation-wise is different, but the context is extremely different. I'm not counting objects here. I'm looking at lengths of them, right? So in terms of this description, we're actually thinking about it in terms of a number line. So on the number line, my object 1, 2, 3, no, 4, was 4 feet of wood. And you could even do it again with concreteness if you wanted to by drawing it out. Like this is my wood, right? And it's 4 feet long. So you can count it like this, 1, 2, 3, 4. And then I have 3 feet of aluminum. And for my feet of aluminum, I have this. And if I keep counting on my number line, I end up at 7, and the answer would be 7 feet. But I'm counting lengths. I'm not counting objects. If a child were counting objects here, what would he get as an answer? 2. There are 2 objects, right? We're not counting objects, we're counting the length of the objects. All right, I have time for one more example before we head out. Less than. For any whole numbers, A and B, A is less than B, written as such. If and only if there exists a natural number K such that A plus K equals B. Let me show you in terms of numbers, because you know this to be true. Why is 1 less than 3? Well, it's because there's a number that I can add to 1 to get to 3, a positive number, a whole number, an accounting number actually. What would that number be? Yeah, it's 2. If I add 2 to 3, they're going to be equal. There is a whole number I can write, or not whole number, I keep saying that, a counting number, a natural number I can write in that blank to make the statement true. That's the definition of less than, using addition, right? We can formulate a very similar description by using subtraction. So if you imagine over here, most of my language is going to be the same. This is the part that will be different. What could I do to A and B to use subtraction to make them equal? Let me use numbers. What could I do to 1 and 3 using subtraction to make these two things equal, the two sides equal? I could subtract the 2 from the 3 side of the equation, right? So instead of adding something to my 1, I could subtract something from my 3. So again, instead of adding something to A, I could subtract something, in particular K, from B, and it would be equal. So the definition I'm about to create is going to have almost all the same words, but this part at the very end is going to have a different looking equation. So it looks something like this. For any whole numbers A and B, A is less than B, written like this: if there exists a natural number K such that A is equal to B minus K. That's the definition, the same one that I just had, but it's using subtraction to relate the two objects together instead of addition. And we will pause there for today.